Hello friends, we'll see the question. Trace the curve r square is equal to a square cos of 2 theta. So as we mentioned, if your given curve contains r and theta, then it's of the polar form. So to solve this one, first of all we'll check the symmetry of the given curve. So what was the first condition? First, just replace theta by minus theta. If the equation remains unchanged, so see here, cos theta, it's an even function, so cos of minus 2 theta is nothing but cos of 2 theta, means you will get an exact equation, r square is equal to a square cos of 2 theta. So equation remains unchanged. So the given curve, it is symmetric about initial line. Initial line represents nothing but theta equals to 0. Now this curve contains even power of r. That means if you will replace r by minus r, again this curve will remain unchanged. So the given curve, it is symmetric about the pole. Now the third symmetry we'll check for. Now substitute theta equals to minus theta and r equals to minus r simultaneously. Then and again the equation remains unchanged. I have given the reasons here. So the given curve, it is symmetric about theta equals to pi by 2, which is in y-axis in the Cartesian form, or you can say a perpendicular line in the polar form. So your given curve, it is symmetric about initial line, it is symmetric about the pole, and it is symmetric about the perpendicular line. And then the next point is, we have to check that either the given curve, it passes through the pole or not. So the condition was, at which angle theta r becomes 0, then for that theta the curve will pass through the origin. That means if I will take theta equals to pi by 4, then it becomes cos of 2 into pi by 4, that is cos pi by 2. So cos pi by 2 is 0. That means we get the value 0. Hence we can say that curve will pass through the pole. So for the angle theta equals to pi by 4, we get the value r is equal to 0. So therefore that curve passes through the pole. Now we have to check for the tangent at the pole. So what was the condition? To find the tangent at the pole, we will substitute r equals to 0. So if you will write here r equals to 0, r square becomes 0. So a square cos of 2 theta becomes 0. So therefore cos of 2 theta is equal to 0. So for which values of theta cos gives 0 values? When 2 theta is equal to pi by 2, 3 pi by 2, 5 pi by 2, and so on. So what is the value of theta you will get? Theta equals to pi by 4, 3 pi by 4, 5 pi by 4, and so on. Then so at the angle theta equals to pi by 4, 3 pi by 4, 5 pi by 4, there exists a tangent at the pole. So how to draw this one? We'll see while tracing. Now the next rule was, we have to draw the table for various values of r and theta. And as I have mentioned in the note, if it is cos or sine function, the angle will vary from 0 to 2 pi. So for the various values of theta, we get, if suppose theta equals to pi by 4, then you get the value of, so if the theta is equal to 0, you get the value of r is a, because cos 2 0, that is cos 0 is 1, so r square is equal to a square. So r you will get as an a, here we will take an positive square root of it. Then if theta is pi by 4, you will get 0. If theta is 3 pi by 4, you will get 0. For theta equals to pi, you will get minus a, and for the remaining values, for theta pi by 4, you will get 0. For 7 pi by 4, you will get 0, and when your theta is 2 pi, you will get the value a. So this is the table which we have calculated for various values of theta. What are the values of your r, and this will help you to trace the curve. So if you will observe, what is the maximum value of r? It is a. And what is the minimum value? That is minus a. So your curve cuts the points a comma 0 and minus a comma 0, and minimum value is 0. Okay, the next is, before going to the curve, just I will see what is the region of absence for the given curve. See, if theta increases, first of all, draw your perpendicular, draw your initial line, that is theta equals to 0, theta equals to pi by 2. This is your pole. Now I will plot the 2 points a comma 0 and minus a comma 0. So here theta will be equals to pi. Now what I said is, you got 1 point here. Now at the pole, tangent will be at pi by 4, 3 pi by 4, 5 pi by 4 and at this point. So I will draw a tangent here. So you have only 2 points, a comma 0 and pole, and this should be your tangent. So this loop will be like this, as it is symmetric about your initial line. Okay, and the same way you got in minus a comma 0, and here it is in tangent at this point. So this curve will be like this, right? Then we'll see what is the region of absence. So as theta increases from pi by 4 to 3 pi by 4, r square remains negative. That means r will be imaginary for this portion. So here there doesn't exist any curve. Again, for the same value, if your theta lies between pi by 4 to 3 pi by 4, your curve doesn't exist. Similarly, for the 5 pi by 4 to 7 pi by 4, again you will get an imaginary value of r. So here also the curve does not exist. Now again, what I told you is you have to find the angle between the tangent and the radius vector. Okay, so to find phi, we have the formula tan phi equals to r into d theta by dr, and it is given, r square is given. Now I will differentiate with respect to theta. So I will get 2r dr by d theta is equal to minus 2a square sine of 2 theta. So dr by d theta will be minus a square sine 2 theta upon r. So r into d theta by dr, you will get minus of cot 2 theta. So tan phi becomes r into d theta by dr, that is tan of pi by 2 plus 2 theta, for we can write for minus cos of 2 theta. So here phi is pi by 2 plus 2 theta. So whenever your theta will be 0, phi equals to pi by 2. So the meaning is tangent is perpendicular to the initial line at the point a comma 0 and minus a comma 0. Now I will show you how we have drawn this. So to complete the curve, it lies between the circle r is equal to a. Okay, so from this we will decide. If you see here, I have drawn the two tangents at a comma 0 and minus a comma 0. Why this happens? Because here theta equals to 0. So we get the tangent perpendicular to these points. So in this way we can draw this curve.